Alright, so everything that we've talked about in the last couple of lessons has led us to this topic here, which is linear Diophantine equations. We all know what linear equations are. They're the equations of lines, and linear Diophantine equations look no different. The only difference is the type of solutions that I want. With linear equations, I want the solution of any point that's on the line, whether x and y are integers, decimals, fractions, whatever, positive, negative, it really doesn't matter. But with Diophantine equations, as you can guess by the discussion of this chapter, we're only looking for the solutions where x and y are both integers. So they don't have a decimal or a fraction attached to them or anything like that. So it's the solutions that we're looking for that makes the difference. All right, so that just kind of summarizes that. So for example, 23x plus 8y equals 4. That's just a standard equation. It looks just like a linear equation. I could find a whole bunch of decimal or fraction solutions to that, but I'm only interested in the solutions where x and y are both integers. So you can kind of go through the whole Euclidean algorithm just like I did a couple of lessons ago. And 23 would equal 2 times 8 plus 7. The 8 would become your new A, the 7 would become your new B. 8 would equal 1 times 7 plus 1. Your 7 would be your new A. Your 1 would be your new B. And so 7 equals 7 times 1 plus 0. Your GCD would be 1. So now I'm going to try and find a solution to 23x plus 8y equals 1. I know that's different from the one that I gave you, but it's going to help us get there. So the first thing I do is I set up an equation where the A and the B are over here and their GCD is over here. Okay? So just like in the last example, I go backwards, starting with the second to last step where the remainder was 1. So I can write 1 equals 8 minus 1 times 7. And so I go the step above that where the remainder was 7 and I replace every 7 with 23 minus 2 times 8. So that last 7 gets replaced with 23 minus 2 times 8. And just like before, the negative 1 gets distributed to the 23 and the negative 2 times 8. So I get 1 equaling 8 minus 1 times 23 plus 2 times 8. And you'll always be expecting this. There's some 8's over here and some 8's over here, which I will collect and make it 3 times 8 minus 1 times 23. All right, so we have a solution to the equation 23x plus 8y equals 1. One of the solutions is x equals negative 1 and y equals 3. I just read that from this equation up here. Okay, so what if I wanted the solution to the equation that I originally gave you, which was 23x plus 8y equals 4? Well, the solution would be 4 times as big, right? So it would be negative 4 as your x and 12 as your y. And if you don't believe me, you can check. I don't mind if you check. Okay? So we set up the equation first where the number on the right side is the GCD. And then from there, I multiply by whatever the GCD needs to be multiplied by to get the number that's actually on the right-hand side. And I multiply my x's and my y's by the same number. All right, so now I have one solution. Well, what if I want all of them? Well, I look at the slope of this line. And remember, the slope of a line in standard form is the negative of the x coefficient over the y coefficient. So it's negative 23 over 8. What that means is if I'm at a solution already, I can change my y by negative 23 and I can change my x by 8 and I'll have another solution. All right. So using my original x as negative 4 and my original y as 12, as long as I go down 23 in the y direction a certain number of times, I would have to go to the right 8 spaces the same number of times in the x direction. So these are all of my solutions. For integer values of n, I can plug in any integer value of n here, and I've got a solution to the equation that I had at the top. So I start with a particular one, and I use the slope to find the rest. All right. Now, it is important to note that, remember I said you'd multiply the GCD by some number to get the number that's actually on the right, that constant that's sitting by itself on the right. But if you can't do that, if you can't multiply the GCD by an integer to get the number on the right, meaning that the number on the right is not a multiple of the GCD, then there's no solution, and that's actually an easy thing to say. So let's say I had this equation right here. I'm going to give you an example. 6x plus 20y equals 17. All right, well, we could go through the whole Euclidean algorithm, and what we would get was a GCD of 2. You already know that. So I'm looking for an integer that I can multiply 2 by to get the number that's actually on the right, which is 17. Well, no integer can do that. So there are no solutions to the equation. Well, there's solutions, but there are no integer solutions where x and y are both integers to the equation 6x plus 20y equals 17. So that's actually a nice problem to have. All right, so what if there's a restriction on the type of solutions that we want? Because when you're dealing in the real world, you may not want negative x's or negative y's. So let's say I wanted the solutions of 50x plus 38y equals 2000, where x and y are both positive integers. Okay? So I am going to have a limited number of solutions to this. So I'm going to go about it the same way. I'm going to use the Euclidean algorithm to find the GCD. 50 will equal 1 times 38 plus 12. So now I'm going to work with 38 and 12. 12 goes into 38 3 times with a remainder of 2. So now I'm going to use 12 and 2. 2 goes into 12 6 times with a remainder of 0. So the GCD is the remainder that I got in the second to last step, which is 2. So now what I do is I go backwards to find a particular solution to 50x plus 38y equals just 2. Remember, I've got to deal with the GCD first, and then multiply by whatever it takes to get the GCD to be 2000, which is actually the number on the right. So, using the second to last step, 2 equals 38 minus 3 times 12, and then going to the step above that, replacing the 12s with 50 minus 1 times 38, distributing the negative 3, collecting the 38s, and I get a solution to 50x plus 38y equals 2. The x is going to be negative 3, and the y is going to be 4. Okay? So that's a particular solution to 50x plus 38y equals 2, and now I need to look at the equation that I actually have where there's a 2000 over here. Well, that just means I multiply my x by 1000 and my y by 1000. So now I have a particular solution. It's actually not a good one because my x is negative. So I've got to go ahead and look at the slope to find a general solution for all x's and all y's. So I look at my slope, and I always reduce my slope to lowest terms, otherwise I might miss some solutions. So even though the slope is calculated as negative 50 over 38, I'm going to reduce that to negative 25 over 19. And so every decrease of 25 in y means I need to increase x by 19 to get to another solution. So x is going to be negative 3000 plus a certain number of 19s, and y is going to be 4000 minus a certain number of 25s, the same number of 25s as there were 19s. So they're both supposed to be positive, so looking at just the x's, whatever n is, it's got to make negative 3000 plus 19n bigger than 0. So that means that n has got to be bigger than or equal to 158. Okay. And then looking at y, that's got to be greater than 0 as well. So 4000 minus 25n has to be greater than 0. So n has to be less than 160. So the only n's I'm allowed to use are n's that are bigger than or equal to 158 and less than 160. So that leaves me with 158 and 159. When n is 158, I just plug that in and I get an x value of 2 and a y value of 50. And then the only other case I have is when n is 159, x is going to be 21 and y is going to be 25. And if I try any other value of n, then either my x is going to be negative or my y is going to be negative. So these are my only two particular solutions where x and y are both integers and they're both positive, and no other solution will do. We will talk about more examples of these tomorrow. If you have any questions, let me know.